Good evening, class. Today is the first recording for our class on differentiation. So, in the class, we discussed about first principles, right? So, let me give a quick recap on what we did in the class and then go ahead. So, first of all, the word calculus. Where does it come from? Well, the Latin origin of this name means pebbles because pebbles were used for counting initially. Calculus also means a deposit of minerals, so like pebble, something which turned hard in and gets deposited in the body. That's also called calculus. But of course, this what we are going to stick to is the definition of calculus as small pebbles that were used for counting. So there are small changes that we are recording in calculus. There are two words that we want you to be familiar with: infinite, which you already know, which means the largest possible number than the known. So whatever is largest possible integer more than that can be expressed as infinite, more than what is countable, right? And we have been introduced to that in several occasions in case of series where it goes to infinity, in case of exponential functions. Some other functions also go, at asymptotes, vertical asymptotes, the function goes to infinity. So we have looked at this idea of infinitely large. In calculus, we are going to look at the word infinitesimal, which means smaller than the smallest possible measurable thing. So very, very small, like in the real number domain. So because we are looking at small changes, we want to work in the number domain, which allows for this kind of small changes. That means as small as possible. So it needs to have infinite significant digits, because I should be able to make go to as small number possible, as small change possible. And therefore, we work in the real number domain. If you see, if you look at integers or whole numbers, from 1 I'll go to 2. I cannot go to any place between 1 and 2. Whereas a real number domain, I can have a 1.0001 or 1.51234 and so on. So I can measure as small possible, and that's why the real number domain, which is also the reason we no longer work with degrees as a measure of angles. We only use radians for angles. Why? Because radians is defined as what? The length of arc divided by the radius, correct? So that means the ratio of two quantities which can be measured in the real number domain by as small possible to as many significant digits possible, and hence the radians is in the real number domain. So we will use all the quantities that we use in calculus are in the real number domain. It doesn't work in the integer domain, because in integer domain I cannot go to infinitesimal changes. Now, why do we need this infinitesimal changes? Today you must have already realized it in the class. So when we spoke about nonlinear functions, we said the whole idea of non-linear means it does not have constant slope, because lines have same slope. So if I move from this place to this place to this place to this to this, I see that the slope, what do you mean by slope? The gradient. The gradient means how does y, change of y, this delta represents change, okay, that's a notation. How does y change when x changes? So my x-axis could be time and the y-axis could be displacement. My x-axis could be space and my y-axis could be amplitude, or loudness of sound or something. So any quantities, what is on x and what is on y, and how does y change with respect to x. So that change is what is not remaining constant. How much y changes at this point is different from how much y changes at this point to how much y changes at the point 3 to how much y changes with x at point 4 to 5 and so on. That's why it is non-linear, right? So I want a method to find out instantaneous changes at every instant. How does y change with respect to x? And the method that is used or was introduced first in calculus was called, that's why it's called first principle. What this method told us is, if I zoom into a region on a non-linear function and I go on zoom in into this. So what does zooming in mean? If I have 2 points x2 and x1, then x2 minus x1 will be tending to 0. That's what zooming in means. I'm going as close possible uh, between 2 points. Alright? So x2 minus x1 is tending to 0. Tending to 0 means becomes as small as possible. So this is an infinitesimal change. And when I zoom in, what I find is this non-linear function appears to be linear within that range of the 2 points. So between x2 and x1, if the difference between them is very, very small, it almost appears like it's a straight line. And if it is a straight line, then what is the gradient of a straight line? Well, gradient of a straight line is y2 minus y1 upon x2 minus x1. Change in y upon change in x. So I can use the concept or the formula for gradient of a line to gradient of a curve if the 2 points are very, very close to each other. Whatever I spoke in English can be written in much shorter form in math. So they say change in y. So instead of delta, I'm using d. dy by dx, the change in y with respect to change in x, is given by y2 minus y1 upon x2 minus x1, provided that in the limiting condition that x2 minus x1 is tending to 0. Well, what is this y2 actually? This y2 is the y value at x2. What is y1? y1 is the y value at x1. What is the other notation of writing this? Well, this dy by dx can also be denoted as f dash x. What does f dash x means? The slope of the function at a given x value. This notation, right, apostrophe kind of a thing, is the representation of change, rate of change of function with respect to x, is given as, in the limiting condition that h tends to 0, f of x plus h minus f of x upon h. So this formula is useful only when the 2 points x plus h and x are very, very close to each other. So in that limiting condition, my derivative, the other name for slope of the curve at a given x, is same as slope of the tangent. Well, actually it is not tangent, right? It is secant, because there are 2 points, x and x plus h. And a line passing through 2 points on a nonlinear curve is actually a secant. But we call it tangent because the 2 points are almost close. So secant looks like a tangent. So a secant, if I draw this, take this point here, it will be like this. If I take a point like this, it will be here. So it almost, after a point, it becomes, the secant becomes a tangent. So the slope of the tangent at x is also known as the first derivative of x and is denoted by this formula. Okay, and in the class what you had done is you used this formula for x square. Fx is equal to x square. So you use the formula. You said limit as h tends to 0, x plus h the whole square. It's a squaring function, right? Minus x square upon h. You expanded the bracket and you proved that the derivative of this function is given by 2x. So you cancel this and you had 2xh plus h square upon h. I could cancel h common between the numerator and denominator because h is only tending to 0 and not equal to 0. So this became equal to 2x. Similarly, you used a similar proposal and said, well, if function is fx, the function is x square, the derivative was 2x. If function is x cube, the derivative is 3x square. If function is x raised to 4, the derivative is 4x cube. Therefore, if function is x raised to n, then the derivative is n times x raised to n minus 1. Well, is this working only for integer powers? Well, I can verify. Let me try for a function which is root of x. That means x raised to half. And I will use the first principle. What is the first principle? First principle says derivative or slope of the curve at a given x or slope of the tangent to the curve at a given x is given by limit as h tends to 0 f of x plus h, means wherever there is x I replace it by x plus h, minus f of x upon h is giving the slope. Well, I'm going to simplify. I want to get the what does the final expression look like. Whenever I have irrational numbers, roots, one trick that I like to do is I multiply by its conjugate. But I cannot multiply the numerator alone. I will multiply the denominator also. And h times square root of x plus h minus square root of x. Okay. The numerator is of the form a minus b into a plus b. So it's a square minus b square upon h square root of x plus h minus square root of h. Well, I can't simply substitute h as 0 till h is in the denominator, okay? Because division by 0 is not allowed. So my whole point of doing this exercise is to get rid of the h in the denominator. That's why I'm doing all this. I hope you understand the point. Limits, you cannot substitute h as, in the limiting condition. That's why it's the limiting condition, that h will be substituted as 0 as long as it doesn't make it undefined. We have done this when we are calculating limits, isn't it? So numerator, and if you see numerator has h and denominator has h, I can cancel it because h is not 0, h is tending to 0. Now I'm left with this. Okay, now can I substitute h as 0? Yes, I can, because the function is not becoming undefined. Division by 0 or 0 upon 0, that form is not there. So I can substitute and I will get 1 upon root x plus root x is equal to 1 upon 2 root x, which can be written as half times x raised to minus half. Let me compare this with the form n times x raised to n minus 1. N was half here. So n is half and half minus 1 is minus half. Oh yes, so it is still obeying that form n times x raised to n minus 1. So it works with any power. It's not necessary that it has to be an integer power. If you don't believe me, try it with x raised to 1 by 3 or 1 by 4 and go ahead. You, of course, will need to know how to simplify them to the roots. As long as you know that and you know the expansion, you can use binomial expansions for fractional powers. You know the binomial expansion for fractional powers. So use that and you can get the result. So it is valid for all n values. Okay. Does it work with negative? Well, let's try. Fx is 1 by x, which means x raised to minus 1. And I want to find out whether this n times x raised to n minus 1 is working with negative powers also. So I'm going to use first principle. So the first derivative, or the slope of the curve at a given x, or the slope of the tangent to the curve at a given x, is given by limit as h tends to 0 f of x plus h minus f of x upon h. Okay, I have to simplify. So I'll take LCM in the numerator. So limit as h tends to 0. X minus x plus h upon x times x plus h upon h. Upon opening the brackets in the numerator, I will get a minus h upon h into x plus h. Well, the h and h get cancelled because h is not 0, it is only tending to 0, and I'm left with limit as h tends to 0 a minus 1 upon x times x plus h. Now can I substitute x as 0, h as 0? Yes, you can, because there is no problem of division by 0. So I'm left with an expression minus 1 by x square, which can be written as minus 1 times x raised to minus 2. Is this n times x raised to n minus 1? Well, n was minus 1. So minus 1 and minus 1 is minus 2. Yes, it is working. So be it negative powers or fraction, this n times x raised to n minus 1 is working. So a good generalization, when fx is a power function, it's a power function, it's not an exponent. Okay, in exponent, what is the form? There is a number in the base and there is a variable on the top. Here what do we have? We have a variable in the base and we have a number on the top. That's the difference between power function and exponent. Okay, don't misunderstand. So what we have derived is the derivative of a power function, not an exponent. So f dash x is n times x raised to n minus 1. This is our first generalized result. And what is n? What kind of a number can n be? Well, n can be a real number. N can be positive, negative, or fraction. Okay. I have other functions that I am familiar with, like exponent, like ln, and I want to explore what is the derivative of each of them, and I'll use my first principle to do that. I'm only going to show you two functions, and then I want to, tomorrow in the class, we will practice a lot more and see how do you work with first principles. So the next function I want to try is e raised to x. Let me first graph this, because I want to understand graphically what is the derivative. So what does derivative mean? Derivative means slope. Slope where? Slope at each and every point along the curve. It instantaneously changes, so I want to graph it. So for graphing slope, I want to draw tangents at every point, because slope of the tangent at that point is the slope of the curve at that point. So I draw a tangent here. Seems like almost 0. Little positive, some more positive, some more positive, more positive, more positive. Ultimately, when it goes, it almost becomes infinity. So it is starting from a very small positive number, almost 0, and going on becoming more and more and more positive till it reaches infinity. If I graph this slope of e raised to x with respect to x, that also looks like this only. Because the slope is starting from a very small positive number, it always remains positive and it ultimately reaches to infinity. So the slope of e raised to x also looks like e raised to x. Does that mean that the derivative of e raised to x is e raised to x? Let me check. So I'll use first principle to verify. Visually, that's what I feel. So first principle says that limit as h tends to 0, e raised to x plus h minus e power x upon h, isn't it? F of x plus h minus f of x upon h. Where has this come from? Again, remember, we started with 2 points on the function. Which function? E power x. What are the 2 points? One is x and one is x plus h. And we took the 2 points such that they are very, very close to each other. H is almost 0. And when we do that, I can use the slope of the straight line as the slope of the curve at that point. So y2 minus y1 upon x2 minus x1 can be used. That's what first principle means. Okay, so I will use my exponent rules and rewrite this in this manner. I want to see e raised to x is independent of h, so I'm taking that out. And what I'm left with is e power h minus 1 upon h. And what happens to this expression when h is very, very small? I want to understand this. Then only I will know what the derivative is. So let me use my calculator a little bit. So what is the expression I want? E raised to h minus 1 upon h when h is very, very small. So go to your calculator, go to menu, and let me zoom and go to menu and go to table, exit and deselect all the functions if you already have something. Too many of them. Okay, and which function do I want to find the values for? I want to find the values for this expression e raised to h. So let me write down the expression. It's e power x. Well, it is h, right? But here it doesn't understand h. So I will write x minus 1 upon x. And where do I want to find this value? I want to set the table. I want to start with a minus 0.001, go till a 0.001 in the step size of 0.0001. Understood? So I'm looking at values of x in the range around 0. From negative 0.001, I'm going to positive 0.001 in the step size of 0.001. Enter and look at the table. Where do you think the values are tending to? At 0 it will give you an error obviously, but where do you think the value is tending to? Why does it give us 0 at 0? Well, you will get 0 upon 0 form. E raised to x is e raised to 0 is 1, 1 minus 1 is 0, divided by x which is also 0, so 0 upon 0 is an error. But at all other points around 0, do you see the values tending to something? Pay attention and you will be able to guess that the value that it is tending to is 1. On the negative side you had minus 0.9997, 0.998 and so on. Positive you had 1.0001 and so on. The smaller that the value of h you take, because h is tending to 0, right, as small possible. See, that's why real number domain. I can take as small a number. Then I saw this whole expression was tending to 1. So what is f dash x? F dash x is e raised to x. This is what I found visually also. I saw the derivative of e raised to x looked like e raised to x, and now for first principle I proved it. Fantastic. I will do one more example and then we will stop. And we will do more examples in the classroom. So I'm starting with f of x as sin x. And in the class, I told you to think about it. That sin x, the slope, what is happening to the slope? What does it look like? So it starts with a positive slope, it goes on becoming less and less positive till it's 0. It's negative, negative, but and then 0 again, and then positive. So positive becomes 0 again, negative becomes 0 again, and positive. So if it is sin x, the slope of the curve looks like it is cos x. That's what I understand visually. Let me verify using first principle. So limit as h tends to 0, sin of x plus h minus sine of x upon h. I know the formula for sine of a plus b, so I'm going to use it. Sine a cos b plus cos a sine b minus sine x upon h. So limit as h tends to 0. I'm combining these two terms, taking sine x outside, and I'm getting cos of h minus 1 upon h plus limit as h tends to 0, cos of x into sine of h upon h. Sine of x into limit as h tends to 0, cos of h minus 1 upon h. We have seen this in limits. Cos of h minus 1 upon h, in the limiting condition of h. If you want, you can verify the same way in tables. Okay, if you want, you can go back to your calculator, exit, go to this function, and instead of e power x, what do you want? You want cos x. So cos x minus 1 upon x. Go to the table and you will see what are the values. Very, very small number, very, very small number. That means it's almost 0. So this entire expression is going to become 0, and the next term cos x into limit as h tends to 0 sin h upon h. You know, in the limiting condition that h is 0, sin h upon h is 1. So the first term becomes 0, the second term becomes 1. So my derivative becomes cos x. So what I saw visually is indeed true using first principles also. So this is where we stop. Tomorrow we are going to practice more on first principle.